Let's take a look at one of the most important theorems or axioms in differential geometric algebra that are out there. So this isn't something that I came up with. This is something that's been discussed in the foundations of Grassmann algebra and differential geometry in various places. But this particular proof that I've constructed here, I haven't seen that before. This is a new way of thinking about this. So in some of the other literature, this is taken as an axiom. For example, an axiom for Grassmann algebra. But in my foundations here, I'm going to look at it differently. I'm going to look at it as a theorem that's derived from the definition of Grassmann and Hodge complement that I've given previously, because in some of the other foundations there wasn't such an explicit definition of the Grassmann-Hodge complement as explicit as the one that I have given here. And so as a result of that, because my definition is much more explicit, I can turn things around and I can make the complement of a complement theorem a thing. Instead of having it be an axiom, I can make it a theorem and look at it from that kind of foundational perspective. And so that's what we're doing here. And I don't think I've seen this particular kind of theorem approved before for this in this kind of way. So how does it work? Well, we'll let omega be a grade M element, and we take the complement of this, and that's supposed to be -1 to the m times n minus m times omega times the absolute value of I squared. This is a fundamental theorem that's foundational and important, and so it's important to be able to kind of prove this and to verify that the choice of Hodge complement that we've made actually satisfies this theorem, and it does. So we can take a look. So let's let omega be a grade M element, and then we can rewrite the expressions using the definition I gave previously. And then what we can do is we can take the reverse of omega and extract out the -1 to the m times m minus 1 over 2. And because we can extract that out, we have a different expression, and we can once again extract out another -1 raised to an algebraic power, and by extracting the reverse operation from the omega times the pseudoscalar. And by doing that, we can now rewrite the pseudoscalar as a square product, and we just have the omega by itself now in the product, and we have a product of -1 to some raised to some power. And this expression can be rearranged by using algebraic manipulation of these powers of -1. And if we write it in such a way that we have -1 times m to the n minus m and -1 times n minus 1 over 2, then that is once again a reverse operation that can be replaced in the, or rewritten in the expression. And so when we rewrite this expression, what is it? Well, instead of I squared, we have the reverse of I times I, and we have this, and the reason we want this is because we can write this as the absolute value squared. And now we have the result. Actually, that is the result of the theorem, and the result follows because -1 to the n times n minus 1 over 2 times I squared is the reverse of I times I, or the inner product of I with itself, or the absolute value squared of pseudoscalar. So the theorem is proved. And we just did it using the foundations of differential geometric algebra that I've presented here. And I don't think I've seen a proof of this theorem using these kind of foundations anywhere else out there in the literature. So I think this is an interesting new way of looking at it and being certain about the truth of this theorem, instead of talking about it as an axiom and having the complement be some kind of mysterious operation. We've changed it around. In my foundational perspective, I have an exact, explicit definition of the Grassmann-Hodge complement, and the complement of a complement thing is a theorem instead of an axiom. So I think that's an interesting way of looking at it. Let's take a look at foundationally important properties of complements, since we've taken a look at the complement of a complement theorem in its general form. There's a more specific form restricted to just the original Grassmann complement. So when we just restrict ourselves to the Grassmann complement axiom with a flat manifold, let omega be a grade M element of Rn, then the complement of that has to be minus 1 raised to the m times n minus m times omega, since the absolute value of the pseudoscalar squared equals 1. The following lemma and corollary are helpful. Let omega be a grade M element, then the regressive product of the pseudoscalar I and omega equals omega. So the proof of this is fairly simple, actually. If you apply the Grassmann duality principle with the regressive product and the exterior product and rewrite the expression as an exterior product, then we can simplify the expression by observing that the Grassmann complement of the pseudoscalar is just 1, and then that means that we are taking the exterior product of 1 with the Grassmann complement of omega. And because we are now just saying that we want the inverse Grassmann complement of the Grassmann complement of omega, this just means we're just asking about omega. And so the result equals omega, and the lemma follows as a result. Now another obvious corollary is that the reverse of omega times a pseudoscalar equals the inner product of I times omega, since I times the inner product of I and omega equals the regressive product of I and star omega, or the Hodge complement of omega. And by the lemma that we just observed, we know that this is just equal to the Hodge complement of omega itself, and therefore it equals the reverse of omega times I, the pseudoscalar, and the corollary follows. So it's just kind of an interesting, obvious thing. Once you know all this thing about the Grassmann complement, the Hodge complement, and these theorems, these kind of things kind of just follow as an obvious result that kind of makes sense once you get into these type of results. It's not just computational language that has to be implemented, but it's mathematical theorems and definitions and axioms that have to be satisfied. That it's necessary to look at the mathematical foundations and the theorems and to think about the proofs a little bit. What that leads to is the design of the computational language that I ended up with, and I put into my code repository on GitHub, Grassmann.jl, and I've now written a paper about it and included a bunch of the theorems, and some of the information discussed in this presentation is all included in the paper about the foundations of differential geometric algebra. It's called Grassmann.jl for a reason, because The emphasis in my program is to try to satisfy the original Grassmann laws and help from that derive the correct understanding, making sense of things in the world. And that's why I created this Julia package, Grassmann.jl, which is available on GitHub. And these fundamental mathematical principles, they're universal, so these things have to be understood before they can be transmitted further, and there has to be a little bit of rigor behind it, and that's why we have taken a look at some of the theorems. I'm just trying to provide my perspective of how the foundations should be constructed for foundations of differential geometric algebra, and Grassmann.jl is a particular implementation of that in computational language, which manifests these abstract concepts I talked about in computational language. And using that, I verify my thoughts about it. Please help sponsor and fund this research and development project. There is a need for funding of mathematical research project outside of academia.